All right, so in the first half, we talked about cylindrical projections. Now we're going to talk about azimuthal or planar projections. These are projection systems that are commonly used for smaller localized regions or even divisions between regions in smaller areas. So maybe for a municipality or a small state. Typically, larger states are broken up into multiple planar projections. So you can see the premise of a planar system is to either touch on the tangent edge of a globe or to intersect that globe in a secant system where you're intersecting the globe at multiple points and you're still projecting onto that planar system. So your distortion in the cylindrical system would increase as you got away from that the parallel around which the cylinder touches the globe, and distortion increases as you move towards the ends of the cylinder. In a secant system, your only really accurate measurements are right around the intersection of the plane with the globe, and your distortion grows fairly rapidly as you move away from that point. So they're typically reserved for smaller areas. So here's one example, which is the azimuthal equidistant projection. You can see here the distortion as you reach the outer edges of the globe. This one is centered around the North Pole. The South Pole is really extremely distorted. So this system would never be useful in comparing areas of different land masses. You can see Australia is significantly expanded, as are the ends of South America and Africa. And then, like I said, Antarctica is just distorted beyond any reasonable relationship with reality. All right, so that was the azimuthal equidistant projection. The conformal projection for planar projections, that this is just one of the examples that we've selected, is the stereographic azimuthal projection, which means that it's preserving the bearing, the navigational aspects of transiting between two different points, but it's not preserving area or shape very well. So in this one, they happen to select a point which is rather unique for mapping off the Cape Horn. So you can see far less distortion in that region of the world than you typically see in mapping. And then this is a fairly famous planar system, equal area planar system, holding the equator as the parallel of no aerial distortion. But obviously the angular distortion gets severely increased as you head towards the poles. You don't see it as much in Antarctica because you don't have a lot of surrounding continents to express it with, but you can definitely see it in the Arctic. And again, this is the TISA's indicatrix of deformation. Each of these indices show how much distortion you're seeing. You have a huge amount of landmass distortion in the equidistant system, and far less so, obviously, in the equal area system. But neither one of them hold the position of the continents consistently, as does the conformal system. Okay, so we talked about aspects just briefly, and so this is going to add on a whole another subset for planar systems because it's something that we use quite a bit more when we talk about planar systems than either of the other two systems. So the aspect is the point from which you as the map maker are observing the Earth and the plane on which you're projecting the Earth. So if you think about this projection as using light rays to project, you have mnemonic systems, which project from the center of the globe, stereographic systems, which project from a point on the opposite side of the globe, and then orthographic systems, which imagine some infinitely distant point from which to observe. So the mnemonic azimuthal projection, one we've already viewed. I don't know if I have the right image in there. I don't. Oh, badly done. I'll have to edit that slide. Let me see if I can bring it up real quickly. There we go. Doesn't look anything like it. All right, so we are observing from the center of the Earth, looking towards the North Pole. And you can see how much distortion there is in this map from that point of observation being right in the middle of everything. I didn't change two of those. Okay, well, good thing we have Wikipedia as backup. The stereographic azimuthal projection, which I think is what this actually is looking from a point further away. So you are going to lessen the distortion towards the outer edges of the globe, but you're still going to have some distortion. So that was the mnemonic. Here's a stereographic. You can see there's less distortion around the edges. I think maybe that was a different stereographic than the one I was looking at earlier. Or maybe I just got all three of them wrong. Anyway, and then there's the orthographic, which is assuming that you are far off in space, looking back on the Earth. You can't see the entire globe because some of it is on the other side, but you're kind of wrapping your viewpoint around. This is the one that we've been staring at. Wrapping your view a little bit around the globe, and you have less overall distortion than those two views. Can I actually get from the center of the globe or the opposite point of the globe. So I will fix those slides and get those reposted for you. But those are the effects of changing your viewpoint. And so this is a similar set of indices for the effects of changing your projection source. So you can see there's maybe a little bit less extreme distortion between the conformal and equal area examples for this. That mnemonic view from the center of the Earth is rather extremely distorted at the outer boundaries, but is held fairly consistent in this, the central viewpoint area, which is the point. So I think I'll just go back through. We have two sections of planar distortion here. We have the selection of how we're going to distort, and then we have the selection of where we're going to put our viewpoint. So there are almost unending options for planar systems, and we use different planar systems in different parts of the world for various reasons. Some of it has to do with how much development of geographic systems your country has been able to invest in. So in some places, you're lucky to have more systems available to you than others. In some places, you use a different one for the municipality of Anchorage than you would for the Mat-Su Borough. And those are all localized planar systems. Okay. So the last piece is for conic projections, and these tend to have fairly specific applications. So if you think about where we saw distortion for the cylindrical and planar systems, where would you expect to see distortion for the conic systems? Might rotate. You're going to see obviously distortion around the edges of the bottom of the cone, but you're also going to see some pretty weird distortion towards the point of the cone. So in a lot of these systems, they don't even represent the North Pole if it's a polar oriented system, which a lot of them tend to be. So they're good for mapping regions that wrap around that center point. So they work well for places like Siberia, Canada, and Alaska. So they're commonly used for Arctic projections. So this is an equidistant conic projection. It's obviously not a good way to represent Antarctica, but it tends to get left out of most of these systems. This is the conformal, so it's preserving your bearing, but not necessarily your distance or your area. This one is a popular one for northern regions, the Lambert conformal. And then there's the Albers equal area conic projection, which preserves area, but not distance or bearing. So you can see the extreme distortion along the poles for the equidistant conic, also the conformal and the equal area. But those two tend to balance some of that distortion a little bit differently. All right, so this is where we're going to summarize what we learned from projections. And that is that there's a lot of different factors that come into play in selecting a projection system. So you have the shape of your system, which is typically the easiest to visualize. You have the orientation of that system, which is whether it's normal, transverse, or oblique. And then you have the type of distortion that you're selecting, which is a little bit harder to visualize unless you draw orange dots all over everything. And tends to happen in the background of the mathematics of how that shape is created and distorted. So does anybody have questions about any of those like fundamental pieces of how we project things before I go on? I apologize, I don't think there's any more Pear Decks. So this is your chance to say what's on your mind or any question that's been percolating. Any thoughts that popped up while you got up and got a drink? Is anybody still there?
Yeah, I'm here.
Thanks.
So maybe this is like really obvious, but aren't you always just going to see the most distortion wherever the plane is furthest away?
Yes, but that distortion is going to appear differently, and sometimes it's going to be really hidden, right? So if you have a system that is distorting your shape or your angle, it's going to be a little more obvious because we tend to have some familiarity with some of those things. But when you're starting to look at distance, it might be a little less obvious. So it's good to understand the underlying nature of your system, and then to be able to tell yourself, this system that I'm using is distorting these features. So I'm going to use it in this case, but not in another case.
Sure. Yeah, makes sense.
But that's a really good question. Any other? Oh, what do astronauts say about projections? I think they say to use the orthographic projection, because obviously if you move further away from the planet, that's what you're going to see. And there are projection systems, and you'll find them in ArcGIS, specifically designed for visualizing the planet from space. And they tend to be orthographic, probably planar systems.
Totally off topic, but speaking to astronauts, if you guys are looking for something good to watch, I've been watching this show called Away on Netflix, and it's incredible. Super good.
Thank you.
Mm-hmm.
I'll have to hit up my roommate's Netflix. All right. Hearing no other questions? There's one more layer to this. You thought you were done. We got through geoids. We got through, what else did we talk about last week? We talked about ellipsoids. We talked about ellipsoids in their relationship to spheroids. We talked about datums. We talked about projection systems. There's still one more layer to this, which is your coordinate system. And I don't just mean whether you're in meters or feet, although that is really important, especially when somebody hands you a points file and it has X's and Y's and no other information to go with them. That your coordinate system is how you quantify all of these projection systems. So you've come up with this mathematical model, and essentially what it breaks down to is going through point by point in your points file, your latitude, or your line file, or your polygon file. And if you're translating between two systems, going through that translation with each of those logged points. That's kind of a simplistic view of what's happening in those translations. So what we tend to do in regional mapping is use planar systems, right? We've got this really great global lat-long system, but as you've seen in a lot of these projections, the latitude and longitude lines tend to get really distorted, and they have less meaning on a local regional level. So we tend to get away from that and start using eastings and northings. So you do see the geographic coordinate system some, which is lat-long, but in the United States, you see the universal transverse Mercator, which is one of those distorted ellipsoid Mercator systems. Or you see state plane systems, which are actually not a planar system. In Alaska, oh, that's UTM, we'll come back to that. In Alaska, we have 10 different state plane systems. The Southeast Alaska uses a Hotin oblique Mercator system. So again, it's a cylindrical system. Zones 2 through 9 use a transverse Mercator system, but the Aleutians use the Lambert conformal conic system. So we're calling them state plane, but they're not necessarily a planar projection. They're just a easting, northing, XY coordinate system applied on a small local level. So the United States has state plane systems for every state. Alaska is lucky enough to get 10 of them. and soon to have more. It's a teaser for future slides. All right, and I skipped over UTM. UTM is a globally implemented transverse Mercator system, and we're lucky enough to be at the very beginning of it. So Alaska starts us off at UTM Zone 1, and then they increase all the way around the globe to come back to the international dateline there with number 60. You'll also see on some UTM grids zones from north to south, and those aren't actually part of the UTM system. They're part of a military gridding system. So when you pick your UTM zone for a map, you're not going to care whether you're in one of the grid zones by the equator or one of the grid zones by Barrow. You're still going to be in that same UTM zone, which would be 4 north or 5 north. There is a difference between 4 north and 4 south, but if you're practicing in the United States, you'll probably never have to learn what that is. Oh, and it doesn't include any regions north of 84 latitude, so don't try to map the North Pole with a UTM zone. Okay. So these are the two that you tend to see most commonly in survey applications. But in mapping, oh, that's right. What did I have here? Okay, so this first one is what it would look like if you use the Zone 1 projection for the entire state of Alaska. And this is why it matters what your projection system is, right? This is what it would look like if you use transverse Mercator for the entire state. And that one's what it would look like if you tried to apply that Lambert conformal conic system from the Aleutians to the entire state. So none of these are particularly ugly, but they're all different for a reason. And that reason is amplified when you're working in that specific area. All right, so the Alaska Albers system is another coordinate system that's used really heavily, obviously in Alaska. And it's especially used by GIS applications for the entire state. So this is what DNR uses for all of their mapping. This is what I tend to use in my mapping template because a lot of the data that comes to me in a 3338 NAD 83 Alaska Albers system. So it's one to become familiar with, learn that number, and start recognizing it in your data. It's also, I think, a pleasing orientation, but that's probably because I stare at that a lot more than I stare at that. So this one looks like Alaska's trying to fall off the map. All right, so now we've covered ellipsoids and, well, we started out with geoids, ellipsoids, datums, projections, and coordinate systems. And the sad news is that all of this is about to change. None of those fundamental underlying concepts is going to go away, but the systems that we most commonly see are going to go away. So supposedly in 2022, although this timeline has been a moving target, we are going to get a new geoid model of the world. And they're already working on that. And they're going to replace NAD 83 with the North American Terrestrial Reference Frame of 2022. So instead of NAD 83, which is hard enough on its own to say, it'll be NATRF 2022. So work on your T sounds. There will also be a couple of other reference frames branching out of N83. Right now we have 3 for the North American continent. Following the 2022 switch, there will be 4. So there will be 1 for North America, 1 for the Pacific, 1 for the Mariana, and 1 for the Caribbean. The piece to note from those 4 different systems is that each of those is either its own continental landmass or is a protocontinent. And so this new system is going to be tied to our continents. So it will be less susceptible to things like continental drift, isostatic rebound from glaciers, changes in mean sea level due to water levels rising, and things like that. Things that are actually happening to our world and have had an effect on the accuracy of that early NAVD 88 and NAD 27 and NAD 83 system that was tied to things like tidal observations and the positions of monuments that have in some areas moved significantly or weren't terribly accurately constrained to begin with. So all of that's going to go away and we're going to have a new system. So the whole new system will be GEOID 2022. Again, unless that date shifts, but hopefully they hold it because I can at least say 2022. 2023 sounds harder for some reason. And the state of Alaska is going to have 19 different state plane systems. And this has actually been put out. I don't think it's been ratified yet, but in March of this year, the bill went before our state legislature to ratify that because we're one of the, I think, 4 states that actually has their state plane system in place under our state law. So we are going to conform with the work that NOAA and other federal charting agencies have done to establish those geoids and datums for the United States, and we're going to expand on that by refining the state plane system. I don't know yet what each of the projections of these is going to be. I haven't dug into that yet, but that will be interesting to see, especially the one that they've done for the Pribilofs and Diomede. It'll be interesting to see how they manage that system. So any other questions on why I've taught you all of this information just to throw it out the window? Probably because we're not there yet, but we will be soon. So it's a really good thing to be aware of. And it's also really important to be aware of the history of how we got there. You can't understand NAD 83 without understanding NAD 27 and the ellipsoid models and the geoid models that predated our current understanding, which we've come to understand wasn't that accurate. I forget how far off. NAD 83 is from the center of the world, but it's something like 4 meters. And to my understanding, that's not something that we can yet really measure well with our current level of measurement. But as things become more accurate and our global satellite networks get better, you will start to see the effects of that inaccurate center of the ellipsoid in the NAD 83 system. So it's time to throw it out and replace it with one that can keep up with modern changes.
I got a question.
Hey.
What company is it where you could, like for surveying and stuff, you could give them your data and they'll post-process it?
So the software that I've used for that is a Planix. I believe Trimble has some as well in their systems.
There's a third party I can't remember what it is, but you give them your data and they'll post-process it.
Which is a
Yes,
federal
that-
system.
Yeah, that's what I was thinking of.
Okay.
Opus.
Yeah, that's actually a federal system, and they take your GPS observations from a static session. So I think the minimum is 2 hours, but they recommend more like 4 to 6. And they take all of the oddities that happen. So when you're collecting GPS data, there's a lot of ephemeral effects of the behavior of the satellites during that time period, and other impacts from the globe. And by recording your static position over a longer period of time, these software systems that Gene was alluding to can average those effects out of your data. So this is one of the things that goes into these more accurate ellipsoid and geoid models, and then adding in the information that we've begun to collect from our global gravimetry measurements, and then as well as a lot of the modeling for things like isostatic rebound and continental drift. They've actually done measurements around Kotzebue. I've forgotten his name now. There was a professor that was putting out long-term GPS static stations to measure movement in the continent around Kotzebue, and there was some early hypothesis that actually might be a kind of a proto-continent in formation. There's beginning to be some rotation that appears to be independent from the rest of Alaska. I don't know the status of that within the last 10 years. I think that was the latest information I had heard on that measurement process. So another really interesting application of GPS data. But yeah, a lot of the purpose of a long-term static session on a GPS is to better constrain your actual point within that satellite constellation. And it's something really helpful to be aware of coming into this 2022 geoid model, because we're going to become far less dependent on the ground measurements and far more dependent on GPS measurements. So there's trade-offs there. GPS is a lot cheaper to implement than a large network ground survey. So when you're looking at modeling a large region or a state or something like that, instead of sending out a fleet of surveyors, you can deploy a fleet of GPS, and those individual GPS are now far cheaper than surveyors. So surveyors are losing their market share to GPS. But there's also a lot of new, interesting, and powerful application that we can do with GPS that we didn't have the accuracy to do previously.
I think you answered the question, or sort of, because my understanding is with the post-processing of the static GPS points, I think they're going to use that for the new ellipsoids and the new data that's coming out.
Yeah, that's a major component of the new ellipsoid. It's also going to take into account those other aspects that I mentioned, the gravimetry and other. I think on. I meant to link, actually. I think they're missing right here. I'll make sure they're in the final slides, but there's some good links from NOAA on their information site on Geoid 2022. And I think there's actually like 8 different factors that they're taking into account beyond, or including GPS observation and gravimetry. that go into this new 2022 model. So there's it's really a huge amount of computer modeling that's well beyond the capability of what we could have done 50 years ago with a pen and paper. My head, I did want to show you guys just really quickly, put this into context in our ArcGIS Pro environment, which hopefully is becoming really familiar looking to you guys. So just a couple examples that I threw in while making the slide for the state plane zones. It's interesting, I rotated one of them, but not all of them. Okay, so this is if you project all of Alaska in zone 1. Got kind of a laid back appearance to it. This is your standard zones 2 through 9 transverse Mercator projection. You'll notice the world gets cut off. Our state plane zone model does not extend beyond those borders there. But the Alaska, or sorry, which one is that? The Lambert conformal conic geoid does, or projection model does. Sorry, even I still get those mixed between each other. And then this is the Alaska Albers, or it would be the Alaska Albers system. What are you thinking about, computer? This computer every once in a while decides that it has to think really hard about running the fan and can't do anything else. All right, so Alaska Albers is a familiar viewscape for a lot of the statewide data. And then these are a couple of my favorite polar view systems. The NSIDC Sea Ice is one of those conical polar models. I don't love the fact that it begins and ends right here through Russia. It kind of does some ugly stuff with some of the Aleutians data. But it's one that's commonly used for modeling of things in the ocean along this area, which isn't terribly well captured in a lot of other systems. And another polar model, the North Pole azimuthal equidistant. So I think this is helpful, especially when looking at northern region issues like subsistence questions, or looking at risks as a result of oil development in the Arctic, or the impacts of a lot of new shipping and visiting tourism to the Arctic. It's good to see those from an Arctic perspective. So this is a projection system that I've started to use quite a bit more in some of my Arctic projects. You'll notice one downside is labeling of web map systems doesn't necessarily respond well to flipping the world upside down in their eyes. So it's good to have things in shape files that you can control. Okay, that is the end of me talking about projections and coordinate systems. Does anybody have any last minute questions or thoughts or questions on this week's lab? Please do remember that this lab depends on you finding 2 data sets in the wild that will work in your map. So it's probably in your interest to either start it tonight or tomorrow if you haven't already, because I think starting it the day it's due is probably just setting yourself up for frustration, because those web systems can go down or not work well or fight you in a lot of unexpected ways, and it's good to have the time to be able to adapt to that.